Test equipment and measurements. Hello again, this is Ron, VK2DQ. Tutorial 27, your self-test drill is drill 21. In this tutorial we're going to be talking about things like voltmeters, ammeters, dip oscillators, ohm meters, and the like, to the level required for the standard amateur radio assessment. Because we're going to be talking about voltmeters, ammeters, ohm meters, SWR meters and the like, I thought it'd be a good idea to give you a little bit about just how those meters work. You won't be required to answer any questions on the operation of a moving coil meter. When you look at an analog voltmeter that's got a needle, and the needle moves usually from left to right, although there are centre reading meters as well, all of those meters work on the principle of the moving coil meter, and this slide shows you a pictorial representation of a moving coil meter. We have a drum of soft iron, very lightweight drum. This is looking end on, so that's the top end of a cylinder, and around that drum there is a coil of wire, and the drum is pivoted, so that coil of wire can rotate in a clockwise direction. Normally this needle would be over here on the left, because there would be, I haven't shown it, but there's a return spring, a coiled spring, which applies a very low, very slight, weak leftward pressure, so the needle sits on the left-hand side of the scale. The scale can be calibrated in amps, ohms, or whatever you want. There's an electrical connection to the coil of wire, so two wires leaving the coil come out of the meter movement, and when we pass a current through the coil of wire, there is a magnetic field created around that coil of wire, so that coil of wire becomes an electromagnet, and here we have a permanent magnet. Think of it as a horseshoe magnet. So there's a south pole here and a north pole there. When we pass a current through this coil of wire, the magnetic field created around the coil of wire interacts with the magnetic field of the permanent magnet in such a way that the drum with the coil of wire on it rotates to the right, and the pointer moves from left to right along the scale. The important thing about moving coil meters is the amount of deflection you get from left to right is directly proportional to the amount of current flowing through the coil. So if you're measuring current and you doubled the current, if you're measuring current and your pointer came up to here, and then you doubled the current, it would go twice the distance. So the deflection of the meter movement is directly proportional to the coil current. It's a simple motor, and the needle can't go past full scale, which is over here, and quite often there's a little stop there to stop it from going past that point. When you remove the current, the needle falls back to the left hand side because there's a little coiled return spring, which I haven't shown, which moves the needle back to the left hand side. A very, very simple device, but we use these over and over again. So you might hear me refer to a moving coil meter. That's what I'm talking about. Nearly all meters, analog meters, are moving coil meters, and it's simply the interaction of the magnetic field around the coil of wire on the drum and the permanent magnet in the meter that causes a rotating force to be applied to the needle, and the amount of deflection that that needle has is directly proportional to the coil current. This slide is of the schematic diagram. I'm just going to change my pen colour, excuse me. This slide is a schematic diagram of an ammeter. Ammeters measure current. Ammeters are often called amp meters. That is incorrect. The proper name for a meter that measures current is an ammeter, double M. This meter movement here is the moving coil meter that we were just looking at. Now, moving coil meters are very delicate things. This one can handle up to 10 milliamps. So we can use them we could use it by itself to measure currents between 0 and 10 milliamps. That'd be fairly useless because we want to measure currents. We might want to measure currents up to 100 amperes perhaps. So what we have to do is to bypass most of the current around the meter. And what I've shown you here is we're measuring 10 amps. So going into at this point is 10 amperes. At the junction here, most of the current will go through this resistance, which is called a shunt. That is something you need to remember. Ammeters use shunts to extend their current range. So if we chose the correct value of resistance here, we could shunt or bypass 9,990 milliamps around the meter through the shunt. 10 amps is 10,000 milliamps. So if 9,990 milliamps was going through the shunt, there would be 10 milliamps going through our meter, and our meter would be measuring full-scale deflection. Full-scale deflection means the meters move from the far left to the far right. And we would have our scale of our meter calibrated so that that point there was 10 amps. When in actual fact, the meter is only able to measure 0 to 10 amps, but in fact we're doing a trick. We're causing most of the current to go past the meter so that we don't burn the meter out, and we're calibrating the meter, say, from 0 to 10 amps. That's an ammeter. Ammeters use shunts. Shunts are always placed in parallel because you need to bypass or shunt excess current around the meter, because no moving coil meter will measure currents in the ranges of amperes. They're all microampere or milliampere meter movements. You can do easy calculations to work out the value of a shunt. There's no need in the standard course. In the advanced course, you do need to know how to do that. But for the standard, you need to know that the way an ammeter or a milliammeter or a microammeter has its range extended is by placing a resistive shunt in parallel with the meter movement. Now, even though this shunt is drawn as a resistor, and all shunts are drawn as resistors, its resistance is incredibly small. In fact, and you'll see some of the diagrams later that I've put in the drills for you for this subject, that some shunts are brass rods or brass bars, because we need the meter is a very low resistance, so we need an extremely low resistance to bypass all of this current around the meter through the shunt. So even though it's a resistance that could be measured perhaps in milliohms. And I've actually seen brass shunts, which are a rectangular brass tube, a rectangular brass plate, and if they're not quite the right resistance, you actually get a hacksaw and cut a slot in the shunt to fine-tune it to exactly the right resistance. Don't cut all the way through, you just cut a little bit out, and that reduces the cross-sectional area of the shunt and calibrates the meter. So that's the ammeter for us. While we're at it, ammeters measure flow. They measure the flow of electrons through a wire. So in order to measure the current flowing through a wire, you have to cut the wire and place the ammeter in the circuit. So the ammeter re-establishes the circuit. Therefore, ammeters should have, ideally, no resistance at all. In practice, they only have very low resistance, and therefore they don't alter the current that we're trying to measure perceptibly. Let's have a look at voltmeters. Here we've got the schematic diagram of a voltmeter. Now we're using our moving coil meter exactly like the one almost that we had in the ammeter. This one is a 10 microampere meter movement. That means it takes 10 microamps through this meter to move it from left scale to full right scale. That's not very much current. But we're not trying to measure current here, we're trying to measure 100 volts with this meter. And you'll notice that this is a series circuit. And the sum of the voltage drops in a series circuit equals the applied voltage. So the sum of the voltages across the resistor and the meter will equal 100 volts. Now the meter may only need a few millivolts across it, and if it gets more than a few millivolts across it, it will burn out. So we need to put a resistor in series, not in shunt. The ammeter had a resistor in shunt. With a voltmeter, we have a resistor in series to drop most of the voltage across that resistor, and just leaving a little bit across the meter, so that if we applied 100 volts, most of that 100 volts would be across the resistor, and there would be enough voltage. If this was calibrated to read a 0 to 100 volts, there would be enough voltage left across the meter movement to give you full scale deflection, full right scale at 100 volts. The resistor placed in series with a meter movement is used to extend the voltage range of the meter movement. Ammeters use shunts, voltmeters use multipliers, and this would be quite a large resistor. If we wanted different ranges, if we wanted 0 to 10 volts, 0 to 100 volts, 0 to 1000 volts, we could easily do that by putting a switch in and putting in a number of multipliers. So we could have different ranges. And we would put a switch in to switch between the different ranges. So if we switch to this range, it might be 0 to 100 volts. If we switch in a different multiplier, we might get 0 to 500 volts, and switch in another multiplier. That's what you're doing when you move the voltage scale on a voltmeter. You're changing the multiplier. You don't need to know about the ranges. You do need to know that a voltmeter should be a high resistance, because if you're measuring the voltage across a resistor with a voltmeter, you put the voltmeter on parallel with the resistor. There's no need to cut the circuit like we did with the ammeter. Let's suppose that resistor was 100,000 ohms, 100 kiloohms. And there are other resistors in this circuit too, and components and things. So there are voltages across them, and let's say you had a meter that was also 100 kiloohms. Well, that would be bad, but because a 100 kiloohm voltmeter in parallel with a 100 kiloohm resistor would turn the resistance in this part of the circuit to 50 kiloohms, and you would get the wrong voltage reading. So ideally, voltmeters should be an infinite impedance. In practice, voltmeters are very, very, very high resistance or impedance. Ammeters, on the other hand, are very low resistance. Ammeters are placed in series, voltmeters are placed in parallel. Ammeters use a shunt in parallel with the meter movement. Voltmeters use a multiplier resistor in series with the meter movement. To measure resistance, we need an ohm meter. Now, voltmeters and ammeters don't need any source of power. The current that flows through them, or the voltage that's applied to them, comes from the circuit that you're testing. An ohm meter, on the other hand, you might be trying to measure the resistance of a resistor. You can't work out the resistance from the colour bands on it. If you're like me, you can't see them. And so you get an ohm meter, and you put the leads of the ohm meter onto the resistor, and the scale is calibrated in ohms. even though I've put an omega symbol in there to indicate that it's an ohm meter, it's just a milliamp meter or microamp exactly like the one you'd find in a voltmeter or an ammeter. In fact, the voltmeter, ammeter and ohm meter can all be combined into the same instrument. Today it's called a multimeter. Once upon a time it was called an avometer for amps, volts and ohms. And today multimeters can measure far more things than amps, volts and ohms. So you can get a relatively inexpensive multimeter that'll measure capacitance, inductance and even frequency. So an ohm meter is a milliamp meter with a battery in series. So in the instrument case there will be a small cell or a small battery and a resistor, because if we don't have a resistor there and we join these two wires together, we're going to have a short circuit and we're going to burn out the meter. And that resistance is adjustable as well, so it's a variable resistance. So if we built this circuit, I mean we could calculate it all out mathematically, but we're not going to go there. I'm trying to give you an appreciation of its operation. And we were to put a known resistance across here, we could calibrate the scale of this ohm meter using different known resistances. And if we were going to measure a resistance, we would first have to join the probes of the ohm meter together and adjust for zero on the moving coil meter. So in order to measure resistance, we need a milliamp meter, we need a battery or a cell, and we need a variable resistance. Three things. And we've got our ohm meter. The purpose of this slide is just to reinforce to you how ammeters and voltmeters are connected to a circuit under test. Ammeters measure the flow of current, so if we wanted to measure, this is a series circuit, if we want to measure how much current's coming from this cell or battery and flowing in this circuit, we would have to cut the circuit at this point and insert the ammeter. That's why an ammeter must have a very low resistance. And don't forget, ammeters use shunts to increase their range of current that they can measure. Ammeters are placed in series because they measure the flow through a circuit. If you're going to measure the flow of water through a pipe, you would have to cut the pipe and put a mechanical flow meter in the pipe to rejoin the pipe up. Voltmeters are placed in parallel. We've got three resistors and we want to measure the resistance across this resistor, say it's R1. We put the voltmeter in parallel and we want the voltmeter to be at least 10 times more resistance than the value of this resistor. That's why it's ideal for a voltmeter to have an infinite resistance. In practice, we'd be satisfied with just a very, very, very high resistance in the order of megohms. Voltmeters are placed in parallel. Voltmeters use multiplier resistors in series with the meter movement to extend the range of the moving coil meter. I would recommend, just as a thought, while I have it, that if you haven't already got a multimeter, go out and buy yourself one. You can don't buy yourself an expensive one unless you've got more money than sense. Buy yourself a cheap multimeter from one of the electronic outlets or eBay or whatever, and if you're unfamiliar with the use of a multimeter, you can get them for about $10 or $12, by the way. You don't have to spend a lot of money. If you want to spend $25, you get quite a nice one. If you spend 10 or 12, you'll get an okay multimeter, and you'll be able to measure amps, volts and ohms and maybe a couple of other things as well. And play with it. Measure the voltage of different batteries, your car battery, the transistor radio battery, batteries out of your calculator, and just experiment with measuring different AC and DC voltages and resistances. And if you blow it up, you've wasted $10, but you've learnt a great deal. For goodness sake, if you're going to be measuring mains voltage, do buy a good multimeter. Some of the plastic on the probes of the cheap multimeters really aren't designed to safely allow you to put probes into a PowerPoint, and you shouldn't be doing that unless you're confident about what you're doing. But there's no harm in getting a cheap multimeter and learning how to measure battery voltage and things that won't necessarily cause you any harm. And you'll learn a great deal from it. And when you've learned how to use your multimeter, then you can go out and spend $70, $80 or $100 and buy a really nice one. I mentioned measuring AC voltage. Well, we haven't discussed how to do that yet, so we might do that right now. Moving coil meters don't measure AC voltage, because if you think back to the pictorial diagram I showed you of a moving coil meter, a coil of wire and a magnetic field, if we were to apply AC to that, then the needle would vibrate backwards and forwards, or attempt to vibrate backwards and forwards with the AC, or not move at all, just sit there and wobble. So in order to measure AC or radio frequency voltages, we need to turn the radio, say this is a radio frequency, so let's say it's 1 megahertz, just for want of saying it's something. We can't apply that AC voltage, that radio frequency AC voltage, to the voltmeter because it only measures DC. But does this circuit look familiar to you at all? I might see if I can sketch a bit of a circuit here. I'm not going to tell you what I'm drawing. I think you've recognized that as a half-wave power supply. And there's the part of the power supply that converts, it's only half-wave rectification, and that's the part of the power supply that converts the AC here to pulsating DC there. And a voltmeter is very high resistance, so this capacitor will charge up to the peak value of the AC. So in actual fact, what we've got there is a half-wave rectifier. So we take our AC voltage, we convert it to DC, and then we measure it. We calibrate the range of the ammeter or voltmeter, because we can measure AC current as well as AC voltage, and we calibrate the voltmeter or ammeter to measure the RMS value. Some voltmeters have this built into the probe leads. It's called an RF probe. Or you can get an RF probe if you've got a multimeter that doesn't measure radio frequency voltages. You can buy an RF probe for it, because these components are so small they can be built into the leads of into the handle of the probe. Please remember that voltmeters and ammeters are usually calibrated to measure the RMS value. The other instrument you need to know a little bit about, and a very useful instrument it is too for amateur radio, is the dip oscillator. I haven't typed the name up, so I'm just going to scribble it up now. It's called a dip meter. And it is an oscillator. It's a radio frequency oscillator that usually has a very broad range. It might go from a few hundred kilohertz up to 200 megahertz. And it is just an oscillator. You don't have to understand this circuit at all. It's a Colpitts oscillator for those of you that are interested. But it's just an oscillator, and this part of the circuit determines the frequency of oscillation. And this coil is a plug-in coil to the dip meter. And there's a meter on the dip meter. And I'm going to explain to you how the dip oscillator does what it does. Just going to pause for a moment and see if I can draw a sketch for you. Okay, it's a pretty rough sketch, but it'll do the job. A dip meter is a rectangular looking device. There's usually a big dial here which determines the frequency, so by adjusting this dial you can set the dip oscillator to just about any frequency you want. This is the meter movement there. I'll explain how what that does in a moment. And to get the full frequency range, this coil here is a plug-in coil. And you'll usually, with the dip meter, you'll have 5, 6 or 7 of those plug-in coils, because one coil will go from 1 to 20 megahertz, another coil will take you from 20 to 100 megahertz and so on. So you have various plug-in coils. And all it is an oscillator, and it begins to oscillate. And suppose we wanted to know the resonant frequency of an antenna. I'll just draw a little antenna, it's a dipole antenna, and we'll put a couple of loops. And let's say the dipole antenna is resonant on 10 megahertz. Well, you think it is. You want to find out if it is resonant on 10 megahertz. And at the moment you've got the dip oscillator set to 8 megahertz. And the needle on the dip oscillator is fully over here. When the dip oscillator is placed close to another device, electrical device, which is on the same resonant frequency, energy will be drawn from the dip oscillator to that other resonant circuit, which could be an antenna. If you were, for example, to get 2 tuning forks, musical tuning forks, I'm not a musician, but if you got 2 tuning forks on exactly the same frequency and struck one and made it sing, and placed it close to, a few inches away from an identical tuning fork, the other tuning fork that you didn't strike will begin to vibrate because it will accept energy from the tuning fork that is vibrating. So energy passes from the active tuning fork to the inactive tuning fork, and they both end up vibrating. That's exactly what we're doing here. If this antenna is resonant on 10 megahertz, and we adjust the frequency, and let's say it's spot on 10 megahertz, when we adjust the frequency of the dip oscillator to 10 megahertz, there will be an absorption of energy from the dip oscillator to the antenna or the LC circuit or whatever it is we're testing, and when that happens, the needle will dip. It'll move left, and it'll dip rather sharply, and if we go above 10 megahertz, the needle will move back. And that's telling us, we read the frequency off the dial, and we look for the dip, and when we see the dip, we read the frequency off the dial, and that tells us the resonant frequency of our antenna. Or we might want to find the resonant frequency of a tuned circuit. We would simply put the coil from the dip oscillator close to this coil and adjust the frequency till we get a dip on the dip meter, and then read off the frequency off the scale for the frequency of the dip oscillator. Quite a handy instrument, very useful in amateur radio. It can be used to measure inductance and capacitance indirectly, because if you know the value of this capacitance, you won't be examined on this. If you know the value of this capacitance but you don't know the value of this inductance, you could measure the resonant frequency of that circuit and then transpose the equation FR equals 1 over 2 pi root LC for L. And none of what I just said is accessible, but it might be of interest to you. That's the dip meter. You don't have to understand its operation. Of the theory of operation that I just explained to you, you don't have to understand mutual resonance. You just need to know what a dip meter does. It measures resonant frequency. It doesn't measure anything else. We can, using little tricks, we can measure L and C by determining the resonant frequency of a circuit. We couldn't measure resistance, voltage, current, or anything like that with a dip meter. It is primarily used to measure resonant frequency. The last instrument that I want to talk about, or that we're going to talk about before we go through some trial or questions on test equipment and measurements, because in this course we've actually covered quite a few things on test equipment and measurements, and so there's no need for me to discuss, for example, the oscilloscope, because we've already done it. But the last instrument I'm going to discuss is the one up on screen, which is the SWR meter, which is the meter we use to determine the impedance match between our transmission line and our antenna, or between our ATU and our transceiver. We would have an SWR meter. The SWR meter that I've put up on screen is a cross needle SWR meter. It's actually two moving coil meters. There's one needle there, and here's another needle here. The great thing, and by the way, this is actually a photograph of my SWR meter, and I love it. I think it's a very, very good meter. It's got a power meter as well. It's got a 20 watt range, a 200 watt range, and a 2 kilowatt range. It measures average or peak power, and it's got no adjustments. You simply, on the back of this meter, there's in and out, and you don't have to calibrate anything, you don't have to do anything to it, or you just use it and read your SWR. But this is how it works, and I'm showing you the cross needle SWR meter because I think you'd be a mug to buy anything else but a cross needle SWR meter, because they're just so much easier to use and so much more accurate. We have one needle here, and this scale is our transmitter power. This is the amount of power that's coming out of our transmitter, and we can set it to be 0 to 20 watts, or we could have 0 to 100 watts on this scale, or we could have 0 to 2 kilowatts on that scale. So this needle will always show us what our transmitter power is. That's the power leaving our transmitter and going to the antenna. This needle, on the other hand, shows us how much power is reflected from the antenna. If we don't have a perfect match at the antenna, some of the energy will be reflected from the antenna back down the transmission line, and this meter will measure that reflected power. The interesting thing about this meter is that where the two needles cross, you get your SWR. Now the two needles are roughly crossing each other there at the moment, and you can see that there's another scale, the red scale, and that's the SWR. I'm not real sure. I think that might be infinite SWR there. I can't tell. I'm just going to have a look at my own meter. Yes, that's infinite SWR. In other words, we're transmitting a little bit of power and getting an awful lot of reflection. So that's a bad SWR. But if the needle's crossed at this position, so if this needle came up to here and this needle came across to there, then our SWR on that scale would be, I can't read it now, looking at my own instrument again, 1.5 to 1. Let me get rid of my writing and then I'll be able to see it. So this is such a useful instrument. So one needle measures your transmitter, so you can leave it in line and monitoring your transmitter all the time. And this scale, the needle will rise and fall as you're speaking. If you're using single sideband, it'll be constant if you're using FM, and it tells you your forward power. This needle tells you your reflected power, and where the two needles cross, underneath them on the red scale is your SWR. Lovely instrument, and they're not terribly expensive. I'd recommend a cross needle SWR meter to you. For assessment purposes, you don't need to know their operation. They're not difficult. Come back and do the advanced course with us and we'll teach you all about them. But I would highly recommend a cross needle SWR meter to you because it's just so much less hassle. Rightio, that's it. We're going to go through some trial exam questions now. Right, we're going to go through section 21, test equipment and measurements. These are not the actual exam questions, but they're facsimiles of them, and they're highly likely to be very, very, very similar, trust me. on test equipment and measurements. The tutorial is tutorial number 27, and this is drill number 21. Excuse me. So test yourself with drill number 21 on your understanding of the tutorials. Okay, let's have a look at it. Section 21.1. To extend the range of an ammeter, it is necessary to use a resistor in parallel with the meter. Parallel is another name for shunt. A resistor in parallel is exactly the same as saying a resistor in shunt. So watch out for that. A resistor in parallel and a resistor in shunt is the same thing. 21.2. To measure the voltage across a resistor, a voltmeter would be connected in parallel with the resistor. 21.3. To measure DC voltages with a milliammeter, it is necessary to place, well, you're using a milliammeter and you're going to be measuring voltage, and that's going to force a whole lot of current, so we're going to need a voltmeter, and we're going to have to place a resistor in series with the ammeter. Where's that? Here it is, the resistor in series, and the name of that resistor, you need to know, is called a multiplier resistor. Question 21.4. The most accurate voltmeters have high resistance. 21.5. To measure the DC resistance of a coil, you would use an ohm meter. 21.6. The extra components required to enable a moving coil meter to measure resistance are, you're going to need a resistor and a battery. 21.7. A simple ohm meter can be made using a battery, a milliammeter and a resistor. 21.8. An instrument designed to measure resistance is called an ohm meter. 21.9. The scale of an AC voltmeter is usually calibrated to show the RMS value. 21.10. To measure current flow in a circuit, you would use an ammeter. 21.11. The instrument usually used to check a transmission is within the authorised ammeter band is a frequency meter. You don't have to know much about frequency meters. Frequency meters measure frequency. A digital frequency counter. They're quite cheap these days too. 21.12. The most appropriate instrument used to measure the frequency of a resonant circuit would be a dip meter. 21.13. A dip meter is commonly used to determine the resonant frequency of a tuned circuit. 21.14. A milliammeter with a diode and capacitive filter is used to measure RF currents or voltages. That's where we're going to, if we're going to measure AC or RF AC, we need to turn it into DC before we measure it. So we use a diode and a capacitor, just like we do in a half-wave power supply. 21.15. To prevent standing waves, a dummy load should be resistive. 21.16. The instrument best suited to measure the RF power from a transmitter is a wattmeter. A wattmeter is just a voltmeter calibrated to measure the voltage across 50 ohms, and the scale is calibrated in watts rather than volts. As simple as that. The moving coil, the cross needle SWR meter is a brilliant watt meter as well. So why would you go and buy an SWR meter and a watt meter? You go and buy a cross needle SWR meter and you've got the whole lot. 2117, an appropriate instrument to measure SWR is a reflectometer. I haven't mentioned that before. A reflectometer is another name for an SWR meter. A little bit of difference between a reflectometer and an SWR meter. A reflectometer doesn't have to have a meter on it. You normally have to attach a meter or measuring device to a reflectometer. But it's not common. I'm not even sure that you might be asked that question. But just remember, a reflectometer, to be sure, a reflectometer and SWR meter are one and the same thing. Think of reflection from the antenna. So it's a reflection meter. 2118. Modulation percentage of an AM transmission is usually measured with a cathode ray oscilloscope, which most people just call a crow. I think this might be the last one. Yes, it is. Not that I'm finding this tiresome. I'm sure you're finding it a little bit more tiresome than me. I only have to do this once. 2119. The waveform diagram below represents an undermodulated AM transmission. And in an earlier tutorial, I do recall showing you what zero modulation and over modulation look like on a cathode ray oscilloscope. You should know them all. Okay, that's it for tutorial number 20. Which one are we doing? Goodness me. Tutorial 27. Don't forget to test it yourself with drill number 21. Cheers for now and thank you for listening and hope your course goes well. This is Ron, VK2DQ.